Okay, right on 6, so ready to start. Hello, everyone. Thanks for turning up again. I appreciate it. It's very late. Hope you're all doing well. Tuesday, kind of had this shocking realization when I looked at this, like at least in terms of lecture counts, I'm like already halfway through. So that's okay, because we just hit section 2. So we'll kind of be a bit into section 2, do a bit more section 2 next week. You have your perspective seminar on that day with Amy. And a bit more of me. We'll get started on section 3 for the end. So section 3 is kind of the bit I like the most. So that's more to my background. So I find that bit fun. About numerical methods. So, and linear algebra. I think you can't overstate how important that stuff is. It's like as mathematicians doing software, especially if you're on the applied side, it's like that stuff's cold. Cool. Oh, I don't think I had anything else to say. There's no admin stuff that I was told about, so that's all good. So last lecture we finished off unit 1 and we got started on section 2. So I'm going to reiterate again. It's probably a bit silly, but sorting's not the interesting problem. The interesting thing is, well, that's laggy. It's taking a while to come up on the screen. Sorry, guys. Sorting isn't the interesting thing. It's the analysis of asymptotics of runtime. So like when you're doing one of these problems, analyzing like, is this a feasible thing to do? Sorting is a really good motivating example. It's easy to understand. The good algorithms are easy to understand as well. So it's kind of nice on both fronts. And the ones you're doing are kind of the state of the art. There's these hybrid sorting ones. I'll probably just go through a little bit of like, when we get up to that bit, like this, there's a zoo of sorting algorithms, of course, because there's like a whole computer science department at every university around the world, and lots of research on this stuff because it's like a canonical problem. For us though, as mathematicians, it's just like a nice motivating example and thinking about asymptotics. Because like you get your wins from dirty tricks and software engineering, but you get your big wins by being clever and thinking about how things are going to scale and how you could rearrange them to scale better. So that's the real motivation for thinking about sorting. Introduced bubble sort last week. It's very simple. I hope you've all got it burnt into your brain by now. It's basically just like go through the array. Every time you see something out of order, switch it around. Go to the end. Go back to the start. Do it again. Back to the start. Do it again. All the way through. All the way through. So that's cool and straightforward. Now here's like I was saying about, you can be faster by doing dirty tricks, software engineering tricks, like layout of memory, the algorithm stays exactly the same. Do some dirty tricks to make it faster. This is an example of that, is this inbounds macro. So talk to you about that. I hope you can remember, do not recommend doing this unless you're very confident that your code's correct. Hopefully in future versions of Julia, this will go away. I think it probably will be where they want it to go. But basically what it's doing is turning off bounds checking for the array. So like you can totally give this thing an index that's outside 1 and the end length of the array, and it will still go there and try something and maybe do something bad. So don't do that. You do get a speed boost though. So in this one, it's, you get this thing of like, you get a percentage increase, not an order of magnitude increase is the takeaway. So you're just changing how the coefficient out the front of this thing scales, not the asymptotics. And the asymptotics are where you really win. Yeah, so that's not super interesting. We did a little bit of lazy timing, not too careful, but you get an idea of how you might do this yourself. With this do timing thing, just for the interest of myself, I'm going to copy this and collect this data again, just because I can. I need a mouse pad in here because it's bench is absolutely terrible. You pain in the bum. Okay. You are making fun of me. Okay, there we go. Okay, we'll go to start a Julia session. Shift plus, Shift B. So while we just wait for that to warm up. Yeah, so I'm going to run that in the background so we can collect that data again. what we're interested in is how this thing scales. So you do a bit of an eyeball test and you go like, well, it's definitely not linear. Like this thing, as I get bigger, it's more than increasing linearly. That's what you look at this plot, your eyeball it, you go, yeah, cool. Not that interesting. We did a hopefully not convincing demonstration that, you know, maybe this thing's scaling quadratically. So we fit a linear model to the data and you can see that it has small residual. And when we try and predict forwards with this model, so like that's a generalization test, like I think it's good to introduce some of this stat stuff because it's like super important. Oh, yeah, again, I've given my background, like the more you think about this stuff early on, hopefully it's interesting. I think this is like one of the most interesting problems in mathematics is like, how do you do model selection, like systematically? Like, how do you tell, given data, what's the generative model for that data? Like, what's the underlying distribution driving that? You know, where you've got all these free parameters. That's kind of what most of machine learning is about. It's just the same thing. It's like seems silly just doing a linear regression. All these things where we're getting super cool results with like natural language translation and neural networks processing images, they're just versions of this in some way. So what's the model given the data? How do you choose the complexity of the model that you're not overfitting the data? Yeah, so semi-convincing, probably, hopefully you're a bit skeptical, like just because it fits. Oh, I didn't say bubble sort. Okay, so function. See if it's in the history. Oh, that would have been easier. Okay, we can run this thing and we get a bunch of times. So plot times. Oh no, it's going to be n range. It's back to front. N range times. We can reproduce the plot that's in the notes, hopefully, bar some timing issues from running on a different computer. Pre-compilation times, we're not worrying about that. The function's fairly lazy with worrying about timing, so you might get some differences. Like here, so on this first one, it was slow. So that was probably like a pre-compilation overhead on that first point. So, you know, then you run it again the second time and it gets fast. It's kind of a normal pattern with Julia. Some funny bump up here, but you know, who knows what was going on in the background. Cool. So we run a linear regression. Ours is not as clean as this one, but we get a similar trend. It's scaling upwards. So what do we want to do? So we predicted forwards. Yeah, cool. Any other ideas about how you might investigate the scaling of such an algorithm? Like, it's like I'd say the engineer's solution for this stuff. Anyone got any ideas? Seeing the model order. If we have something that we think is some sort of polynomial, how could we plot the data to display what the order of the polynomial might be? Yeah, plot it on a log plot, see what happens. So like if you've got something that's a polynomial and you take a log, power goes out the front, so that becomes your coefficient of your linear model. Great, awesome. So yeah, can't get enough log plots. So over here, we've done a similar kind of thing where we divide it by the power. And you show like, it's kind of flat if it's a power of 2. It's this growing thing if it's not the power of 1.8 for reasons. We picked 1.8. So, you know, it's kind of flat if you divide it by a power of 2. It's probably a power of 2. So, yeah. So, yeah, it looked, you know, looking at this thing, it looks like it's scaling as a quadratic and like, yeah, cool. So you'll see this order, big O notation for the asymptotics. So like if we say n is the size of our array, some order of n squared. So there's kind of families of these things. What's the most interesting for you guys is like the worst possible case is like exponential growth. So, well, it's not really the worst. You could do worse. You could have a n to the n or n to the n to the n to the n if you tried really hard. I guess the one I think about as a maths background person is if you think of sets. Everyone done a bit of set theory? Not really, maybe second year-ish, right? Some of you. Set theory. So if I have a set of size n, what's the cardinality of the power set of that set? Is anyone going to say? 2 to the n, yeah, right. So like, this is like an idea that this might be the worst possible outcome. If you have to take the set of all subsets of things in the set and check them all one at a time to get the answer, you're going to get 2 to the n scaling. So like big classes of important problems do have that sort of scaling. Unfortunately, this is the world we live in. Or nobody knows an algorithm that's better than that. So like I was just saying about Polymathian, like being an optimization consultant, they do mixed integer linear programming. So is that anyone's done any operations research? You, maybe a few of you. You'll hear of that. It'll come back again. Like that's like there are these software libraries that are very, very powerful for doing mixed integer linear programming, even though they still scale very badly. They still scale exponentially. You can do clever tricks to cut out big parts of the search space. So they're still exponential. They still scale like the worst possible way they could, but the coefficient gets smaller. Important class of problems for, and anyone want to say, anyone know the prototypical example is traveling salesman problem, I would say. So that's like, you've got a bunch of cities, you get to visit each one once, and you've got to find the shortest path to all the cities. Or you visit everyone one time and come back to where you started, is the usual version of this. So this is actually practical at one of the, these sorts of operations problems turn up all the time. Like nearly every business problem is this one. So I used to work for a place that did remote aerial surveys. So they'd fly a plane around, and you've got to find some stuff that you're going to scan. In this case, it was power lines. So we used to fly around and try and scan all of the power lines in Queensland. So you've got this question of like, I've got some airports, got some power network in between. How do I plot a path so that I'm going to cover all the places where there's power lines and get back and use the least fuel? It's like, you can see straight away, there's like, oh God, like there's all these combinations and I've got to kind of check them all. How can I cut that search space down? So the usual answer when you're in industry is like, you do something bad that's good enough, that's quicker to solve. You could go and brute force. So like, this thing of operations research and trying to solve these big problems. Like if you were someone like Qantas, where you've got to like plan routes and stuff, and like, how do you optimize which routes you're going to fly on given the number of passengers? It's like, it immediately turns into those problems all the time. So they're super important. But so even though they suck, sometimes you have to solve them. When you're in normal software engineering land, usually you'll see problems that are like n squared, n cubed, they're sort of semi-practical, a lot of the linear algebra stuff. So like if you're doing a least squares problem, you have a matrix, like a square matrix of size n, doing something that's kind of like the order of n cubed for doing matrix solves comes up all the time. And that's useful. Again, how do you make that quicker though? Like it's always this pressure of like, what clever tricks can you do to make this process faster? All the good ones are less than that though. They're all like, all the famous ones, like if you have something like fast Fourier transforms. Anyone heard of that? Fast Fourier transform? I'll come back to it again later because I'll talk about it a tiny bit, but super useful algorithm for digital signal processing. It's like everywhere. It's like, even if you look at a JPEG image, it has not an FFT, but something, its close friend is used for image compression, which is something I might talk to you a little bit about later when we get to the linear algebra section. But so it's this super useful algorithm. It has n log n scaling. And then if you're really lucky, linear scaling. If you're really, really lucky, log n. If you're super lucky, it's just a constant lookup. It doesn't depend on the size of the thing, the problem you're looking at. You get those things too. That's just like survey of all these things. We'll talk about once things that have order one lookup, lookups being order one, and some data structures. This will come up in this lecture. So it's kind of sort of going slowly through this first bit, but it's like, all this, for some of you, this stuff's going to be new, but I hope it's really obvious about why it's n squared. It's basically this double loop. For I in 1 to n minus 1, for j in 1 to n minus 1, that's basically a product. You're going to go through the inner loop, the fast loop here, n minus 1 times, then you increment this one, go through it again, take the product of that, blah, blah, blah. You should get something that's half n squared n minus n minus 2, which is the order, we're just worried about the biggest exponent, order n squared. Hopefully that's obvious. Anyone want to guess which line's slow in that? Like what's the rate limiting step of this algorithm, just using intuition? Sorry? What line number? Which one? Can you see that? 2? More so the stuff inside. Like this is where it's actually doing stuff, like it's actually going through an array. This bit will be fast, like getting these indexes will be super fast. So I guess it's between line 3 and line 4. Which one's going to be the one that sucks? Actually, it's actually 4. It's 4 because you're getting something out of memory and putting it somewhere else. So this bit, you're just getting something from memory rather than changing it around. If you do timing of this, you'll see that this bit is super fast. And it might be something if you're really canny, you might have seen it when I was demoing bubble sort last week. If I didn't reset the data array, did anyone notice what happened? Nobody was paying attention. I was paying attention because I noticed that I had to go, oh God, I got to keep remembering to reset this data thing before I do timing. Let's just do it. I'll go data equals rand, not too big a number. Okay, at time, bubble sort. 0.3 seconds. Just do it again, just so something around that time. So there's a little bit of non-determinism depending on the data we have inside. If I run it again, like twice as fast, 3 times as fast. That's because when we look at this, it's like empirical proof. I don't know if that works for you guys because you're mathematicians. If you're a physicist or chemist or something, that would totally work. But we're only hitting this condition, right? And then we're skipping over it. So you're not doing the second step, and that's taking up most of the time. That clear? Making sense? This is like when you're starting to worry about performance stuff, kind of nitpicky into the little things you see. So so a little bit of code here. Again, we're just going to put a counter. So it's the same thing. Like these are the kind of things you'll do when you're debugging. You might want a little thing that's just going to count up how many times something happens. So I won't belabor this by going through it, but we're going to put in a little k equals 0, and we're going to increment it every time we hit into the middle bit. And we should see that that equals this little equation that was derived above, n times n minus 1 divided by 2. And it was 28. So again, little empirical proof that a little bit of analysis of how many times it's going to go through that tight inner loop is done. But as we said, like it depends on the data, like how many times you're hitting this condition, will influence the speed time. So it's actually a function of the data, how fast this thing will run in practice. Clear? Cool. Following along, I like it. It's good. Does that give anyone, just like, see who's got really good intuition as well here? Is there anyone, can anyone come up with like a little trick we could do straight away to make this faster? Can anyone see what might be a little trick you could do in this case for bubble sort? Yeah. So again, so that's right. Like if you go through it the first time and you never had to swap anything, don't do anything. It's like it's already sorted. So that's like if you're trying to do an optimization of bubble sort, that's the optimization, and that's like the best possible case. It's like when we talk about analysis of algorithms, you're going to get best case, worst case, average case tend to be the types of analysis people do. You probably care about average case most of the time. So that's an example of like when I was saying about these ones that scale horribly. There's lots of useful problems that have horrible asymptotic scaling in the worst possible case, but the average case is nothing like that. So it's still practical and feasible to do these problems. Interesting. Another, I guess I'll say a little bit about it. Another interesting case is like relaxing exactness. Like you can often relax how close you're expected to be. So like you could imagine a weird sort of probabilistic version of this where you go like, oh, it's almost sorted, probably like 99% of the time it'll come out sorted, or 99.99% of the time. And, maybe you get linear sorting, and maybe for your application, that's okay. So like stuff's all very application specific about where you want to go with it. And lots of interesting questions about where you might go with it. So I got a question in the chat, it's very long. So in arrays, when you switch elements on the inside, assuming it's time array, it's XON, right? You have to recreate the array each time unless the vector is implemented in some other way. That's a good question. That's to do with the internals of the specific language. Good question. Not so much in Julia. It's not actually doing reallocation, I don't think, but you'd have to do careful profiling to check with that one. But for this one, no. I'm pretty sure it's definitely not doing any reallocation, but pretty sure, like, again, I'm like one of these probabilistic sorting things where I was like 99% of the time. I think that's right, but we'd have to be careful to check. I'm gonna probably, yeah. So yeah, in different languages, you'll get different behavior. That's true. So depending on how it's passing variables around. You can actually see that with garbage collect, with one of these things that comes up with timing. You would have noticed this sometimes. You'll see this little bit of logging where it's doing allocations. This is saying about whether memory allocations are happening or not. So it's kind of like on the first go, yes, other goes not so much. So if you were looking at, there's like an empirical test for whether allocations are happening. There might be something to do with that. And memory allocations are the things that make, as the big thing that makes things slow. In Julia, you get the special one of type instability as well. Okay, cool. Cool. So this stuff's just like, I think I showed this last time, is like, if we look at the documentation of sort itself, you've got some array, says about the algorithm. I got this question about how many algorithms are supported. I meant to go and check it up, and I'm very sorry I didn't. I suspect it's very limited set, because it's like basically the answer with these algorithms is quick sort, merge sort, tim sort are like the three that anyone ever implements, because they all kind of just do that because it's the best. We've got this LT less is less, by equals identity, ever equals true, order equals false. The thing I would say is to look at the design of things that other people have written who kind of are more experienced. Like when you're going to go and make a function that does a thing, you'll get a big hint about what they've learned from the interface of the function. This is like more advanced than probably I should be talking about to you guys, but this is like a practical thing of like, these are things that either the person who wrote it thought they would need, or people have asked for. Like, I would like to be able to do this where I just flip the order. So that's that rev one, or I'd like to use a different comparator. So if I'm just looking at less than, I'm going to use is less as a default, but maybe I want to do something else. Maybe I want to do something slightly weird. Cool. So anyway, that's what I was just going to say. So we see this little example of, again, I'm not going to belabor this one, but this is useful, is this is given a comparison function here. Bubble sort with an optional argument with comp, and it's going to go comp equals greater than. So we're actually passing, I love the thing that to notice here is that, you know, what is this guy? What is that? Well, as an object, like, what's that going to be? It's probably a silly question if I don't give you enough context. If I go for the help for that, it's a function, right? So I can actually pass a function as an argument to another function. So like same way we did recursion, the thing you can do in languages like this is you can pass a function as an input. So to make this much more flexible, we can pass different types of functions in. So comp will get switched out. So you could use a totally different thing than greater than. You could swap it around for less than. So if you wanted to do this guy, bubble sort, we're going to go data equals 1, 2, 3, 4, 5. Bubble sort data comp equals less than 3, 2, 1. You can flip it around. So I can pass a function in, different function in. Anyone want to try something super weird and do sign? It's not going to work because it takes 2 arguments. Anyway. What would be one that takes 2 arguments? I won't do that. Sorry, I'm being silly. Okay. So that's like, this is like a hint to the flexibility of these dynamic languages. Like you can pass a function in as a as use it like a variable. Sign doesn't take 2 arguments. That's why it crashed. Yeah. So like, I was just trying to be silly and go like, oh, it's going to be a thing that takes 2 arguments. I'll just pass the thing in. I couldn't think of a function off the top of my head that takes 2 arguments that I can put in instead. But could try any old crazy thing. Tempted to talk a little bit about, no, I'll leave that maybe later. That's maybe later. Okay. I think that's super cool though. This is the power of using dynamic languages. Yeah, you could pass if you want to try something crazy, you could do an anonymous function where you could go x goes to, oh no, I won't do that. But anyway, blah, blah, blah. You could write another function that passes that in. I won't go too far. Okay, so yeah, so you could, this is a kind of crazy one. Please don't do this, but you can do this where it's passing a comparison function and it's also passing in a global. This is like one of these things you shouldn't do, but it's like practical in the notes to just do it. So make it easy. Or sometimes when you're doing a demonstration, like globals are generally a bad idea. Like sort of software engineers shudder if you see someone using globals too often, because it's like they have long range effects that are hard to predict. So like if you're using this bit of code that changes somewhere else because it's a global, it can change anywhere in the function. Please don't do that too often, but sometimes it's cool to watch. It's kind of this is an example of this two arguments. So this is an anonymous function with 2 arguments. This was the kind of thing I was going to do, but you could pass a comparison function that takes n1, n2. This one's doing the sum of the digits of n1 and the sum of the digits of n2. Cool, that's a crazy comparison function. That was a good one. There's one in the notes just below. I didn't need to do so. You can see something bizarre. So you might need to do this for your problem. It's really about types. I'm going to talk a little bit more about types. Types are super important, super subtle, I would say. Most of the things that I don't have a good spiel on that, but like as a programmer, you're mapping a real world problem to something a computer can deal with. One of these, the crucial part, I would say, is the data model. How do you take a real thing, turn it into a thing you can use on your computer? It's not just integers, it's not just floats, it's not just arrays of floats. You know, if you're a mathematician, yeah, most of the things you do will be that. It gets more complicated when you're dealing with an employee. Like, what's an employee? How do you parameterize an employee and pass that around? You know, that's complicated. And this is this thing about types and type systems. And one of the features I was saying about Julia is multiple dispatch. Maybe I'll just do a silly little quick demo. This will come back. Andy's going to talk more about this in section 4. The natural Julia thing is not necessarily to do passing this function around. It's actually to use the type system to do a better job. And this is something that will give you lots of flexibility. So if I make a struct, so this is how you make your own custom data type in Julia. And I'm going to go, it's a person. They have an age. That's a float, 64. And they have a name. That's a string. End. Cool. Now I can make a thing called a person. And I give it 2 arguments. So its their age is 23.3. Name is Amy. Then you got Kevin. It's a person, he's 32. If I was clever, I would have made a constructor for this that was a bit better. So now made a person 32. In Julia, I can make an array of Amy and Kevin. It's a 2-element vector of type person. So this is this new type I just made. Cool. Now I can do this little trick, is less X type person equal, oh, sorry, I'm doing a one-line function here based on my types that I just made. I'm going to go x dot age y dot age. So what I'm doing is I'm saying a new method for base, so base Julia's is less for my type. This is a new version of this function for my type. What I'm going to do is get their ages and say person A is less than person B if their age is less. That's very ageist. I'm very sorry for that. So what's kind of magical is now, like, without writing any more code, hope this works, I can sort X without having to do anything special. All I had to do was say what is less is for type, for this type, what that actually means. Is that confusing or useful? This is how you can write lots of code with a very little amount of code in Julia. This is like the magic feature of Julia, is this being able to do multiple dispatch. So this is a small hint and it's really subtle. You have to think about data types. You have to think about how you, this is like more advanced, but it's just a little hint of what's going to come up. Anyway, I just thought that was useful to show. Okay, again, so I won't reproduce this plot, but I'll just talk at it. What we're going to do now, we did this timing for bubble sort. Cool. How much quicker? Let's just do it empirically here. We're going to go data is that. We're going to go at time. Cool. I go data equals that. And we're going to go at time sort. There's an in-place sort too. Oh, did I do that wrong? Sorry. Yeah, so, okay, so it's a hell of a lot faster. The inbuilt sort is doing something very different. So if we do an equivalent plot for sort using the built-in sort, you'll see that, like, instead of being, when we were looking at this previous plot right up the back, right up the back, like it's taking like 100 over this range. When we get down here, it's like down to less than, it's like over 100 times faster, 200 times faster. Absolutely crazy. And the asymptotics look kind of different. So it's a small sample. So, you know, like up to 10,000, it's like, it's slightly curving away and there's a bit of noise in there, and because we've done the lazy version of the time. Yeah, so, but it looks like it's like a little bit more than linear, but not quadratic. So that's a hint that something's going very different, something very, very different is happening underneath. And these sorting algorithms, we're going to go through this, we're going to get to this point, is that they're actually scaling like n log n, which is so much better than log n squared. So hopefully you can see that, like just mathematical intuition, that this thing's scaling way better. The kind of feasible range of arrays you could sort is so much bigger if you get that sort of scaling. So you can go to much, much bigger problems. It's actually, so it can be proved for arbitrary data, you can't do better than n log n. For specific types of data, you can do better. So if you know something, this is a general point about all these algorithms and asymptotics, and I'll say it again and again when I get to the numerical methods bit. Just because something has good asymptotic behavior does not mean it's perfect for your problem. If you know something really special about your problem, like say the distribution of the data. So like, let's say, you know, let's try and think of a weird stochastic process where you know, like you've got an array of length 1,000 and something about the distribution says that one of those elements will be 1. Like maybe the way you would sort that would be very, very different than using these sorting algorithms. Maybe you do something really special instead. So like it depends on the distribution generating your data. For arbitrary data, you do these asymptotic things and you go like, can't do better than n log n, but you can in principle do better, especially if it's like discrete data. So like if the data can only take on specific values, there's a lot of special tricks you can do there as well. So yeah, one of the ways to make algorithms fast is something called a data structure, where you're going to burn a bit of memory to lay out your data in such a way that it makes the problem you're trying to do easy. That's the kind of general idea of data structures. It's like, it's a special model of the problem, of your data for the problem, that will make it easy to do particular things. It's make it very easy to do the wrong thing. Like if you get it wrong, like this is, again, data modeling is a really complicated problem, not solved, I would say. Like how people think about how you model data is like the most usual thing you get wrong in software engineering. Yeah, I don't know if I'm harping on too much about that, but we're going to talk about data structures. We're going to go through some of the basic ones. You've seen this original one already, but maybe not thought about asymptotics. For this one, is talking about an array. So array is like the basic thing that's like the next level up. As soon as you got numbers, you're going to put numbers in a bucket, right? Like, and they're going to have a special ordering. So there's going to be a first and a last, you know. Depends what type of maths you've done. You go vector straight away, nearly, but vector's got like a special property extra. We were showing that yesterday with like transpose. So, man, yeah, you've seen that stuff. That's boring. So the thing to know here is that this is an example where you've got, it doesn't depend on the size of the array, in quotes. Does a bit, like maybe if your array is from here to Jupiter, you know, like if you had a very, very big array that you can't fit in memory, that's not going to be true. Up to the size of your memory though, lookups are constant time. So this thing of like going like, if I go XX equals 1, 2, 3, 4, I want to see what the fourth element of XX is, doesn't depend on how long XX is. You know, if this thing was 1 million length long, it would take exactly the same amount of time as it would if it was like really short. So what's useful to know here? That's super useful to know. But you know, then you have the same problem that we're looking at sorting for, is like finding a thing in the array, like a particular thing. If you go like, I'm looking at the fourth place in this array, but I want to know if like, how many things are greater than a certain number, or if a particular value within the array exists, that's not super fast, right? So like if you are solving a problem where like the existence of a thing in this data structure, and you want that to be faster, you maybe use something different. Is that a clear distinction for people or a bit weird? We'll talk a bit more about it. It'll come up. Useful thing to know, this like is super useful, L-type data. Maybe it's not clear. L-type data, L-type of an array will give you the elementary type of the things in the array. So if you've got this array and you want to know something about it, this is another subtle one. If you're trying to make code go fast in Julia, you have this problem of type instability. You may or may not have run into it. So typical example, I was trying to think of an example for you before of type instability. This would be the perfect one of like, if I'm going to pre-allocate an array to do something, if I'm going to make a function where I take an array as input and I'm going to make a result that's say the same size, I might want to pre-allocate that array. If I pre-allocate the wrong type, the code's going to go slow. Well, I'll do it specifically. This is like a really stupid example, but bear with me. I go y equals zeros length x. This function is dumb, make no mistake. Or I equals 1 to length x, y I is xi. But just as an example. So if I go make copy xx, it'll return yy. Did anyone notice the difference between what I just made? So let's go yy equals that. What's the difference between those two things? Can anyone see it straight away? Yeah, specifically, what is it? Yeah, that's right. So if I look up the help for zeros, the default type for constructing zeros is a float 64. So back to this function, it's particularly this line. If I go y equals 0 is length of x, this thing's going to be a float array. And so this thing's actually not going to even be the same thing as this. So if I go, oh, it's true. Well, that wasn't the example I was. You get these things. Anyway, it's a different type, but it's saying the same. Anyway, I should have pre-baked this one. But point is, this is a super useful case for L type. If you have a thing where you're doing something like this, if you put L type into zeros as an argument, L type will give you the type of the element of the array. If we run this guy, now they're integers. So you're going to make an array of zeros of the type of the thing you put in. Cool. Well, maybe useful, maybe not. Hopefully that's not too weird. Oh, now let's get, this might lose some of you, but Julia gives you lots of information about the low-level stuff that's going on, whether it should or not. It's pretty weird to have to use a pointer in Julia. Like, this is not normal. This is just so you can see what's going on underneath. So what this would do, and say this, so like we've lost all this abstraction. It's not just like a programming language, it's all dynamic types. We're going to go, okay, go to the memory address of that bit of data and give it back to me at that index. Yeah, there's some stuff here. It's unsafe. Be careful, Julia reference area exists. So you can do some stuff with pointers that you're probably not meant to, but you know, Julia's not going to take, the creators of Julia aren't going to take that control away from you. You can do this stuff. What we're interested in is like the layout in memory of an array. I'll talk more about this when we get to multi-dimensional arrays, because it's probably more important there. But you can, if you so wish, you can get a pointer to the object itself. What do I call it? XX for mine. Pointer to an int. We probably want to do a, what are they giving for an example here, so we're not too far away from the array? Oh, they're ints as well, that's fine. Okay. You can get a pointer to the data type itself. We can go to the index of the first guy. That's the same. We can go to the second one, third, and length, XX. Okay, so like this is where it is in memory. And anyone, maybe our example's not so great. Oh no, it's not too bad. You can see that there. So how far apart are we seeing those? Those things should be a constant number of steps away if we're thinking about this as like, you know, so many bytes away. All these things will be laid out in memory right next to each other. Anyone know why that would be? Yeah. Yeah, that's right. There's another reason as well, like having things close in memory. Memory locality, if you have bits of data that are from the same object close together in memory, access to them will be faster. So even though it's random access memory on your computer, that's why it's called RAM, like kind of this deterministic pattern will make it faster. Like reading stuff that's close together in memory will be read through faster. So this is one of these examples. I go back to the start where I said like computers like this pile of abstractions, but sometimes the low level details of the implementation matter. This is one of these ones where it matters. So like if you want it to be faster, you put stuff that you're going to use together in memory, close together in memory address. So it's faster at accessing it. Okay, it's a little bit weird. How much time? We got time, that's good. Okay, now we're going to go up a dimension. So we had vectors. We're thinking like mathematicians. We went scalars for the first bit, vectors. Next thing is the hierarchy of these things. Matrices, and then what is above that? tensors or multi-dimensional arrays, multilinear arrays, blah, 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 whatever you want to call it. So multi-dimensional arrays, Julia does this. If you're going to make a matrix, oh, I don't want to say that. So like we could just go A equals zeros, 10, 10, makes a matrix. You can also do this. Ooh, now you can't even look at it. But so that's like you can keep going and keep going and keep going. You'll fill up your memory really quickly if you keep going up with dimensions, as you should expect, because this is one of these things that scale really badly. As you guys start going to higher and higher dimensions, things scale very poorly. So we've got a little, I didn't want to show this one straight away, but if you want to allocate an array without, so like I did before, I did an allocation where it's zeros because I know I'm going to write over everything. If you want, a better way to do it is to do this little syntax here. It's an array. This is the type. So if we want to do int 8s, we put it here. And this is the dimension of the array. So if it's a matrix, it'll be 2. It's this other tensor thing, whatever cubic thing you call that, that would be a 3. And it's of type with undef. So if you look at the data, it's just like random shit that was in memory. So like that's what undef will do in typically. So like that's a quick way of allocating an array. I tend to bad habit of always doing it with zeros, but please don't do that. What we're going to do if we run through this one, we'll go through and you'll see again that this is something that's kind of weird. It's like you can do a linear index into the array, even though it's two-dimensional. So you might think if it's a matrix, I want to go like IJ, you know, like 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, blah, 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 blah. Keep saying that for half an hour. You can do this index into the array like this. You can go like, and pick out the data. So like that's a hint that there's a special ordering within this array for how things laid out in memory. And this has consequences. Like this is again, another case where there's something about computers that will make a difference that you kind of hope it didn't. So again, we've got the same pattern that we stride through. This is a different data type. We've got int 8s this time. So nice thing about that is these guys will all be 1 byte apart. So it's going 38, 39, A, B, C, D, E, F, because it's in hexadecimal, then back to 1. This guy will click up 1, blah, 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 counting up. So if we want to see how that's actually happening though, like if we're doing this linear, we can also do, sorry. We want to see how the data's, if you iterate through what you get out, blah, blah, blah. That's not so fun. So again, the thing that's interesting here is like array access is order 1, but does anyone want to guess what's going to happen? So like there's actually an order, a particular ordering that you go through if you're doing this linear mixing in the array. Is that showing that? I don't know if that's what I want to see. Yes, this is exactly what I want to see. So we've got this data matrix 1, 2, 3, 4, 5, 6. So it's going as you go down the rows and across the columns, it's counting up 1. And that's actually how this linear indexing into this array is functioning as well. That's what this little snippet of code is saying. We're looking into the array with the linear index and we're looking up with I and j. So we can see what I and j map to. So j is the outside one, I is the inside one. And we can see that, you know, it's different. It's how it's actually doing this column major thing. So this actually has a consequence that's really kind of annoying. What we're gonna do, we've got 2 separate functions here. Take the data, and we're gonna go through it in 2 different iteration orders. I hope you can see this. I'm gonna sum over the rows first, and sum over the columns first. So like this would be, so like I'm gonna go sum this way, iterating this way, or sum iterating this way through the array. Like you would hope they both have the same asymptotic complexity, that doesn't make a difference, right? Like they're both order 1. But we saw that there's like, some of them are really close together in memory. Then when you go down to the bottom here, they're going to jump up. There's going to be a big jump. So if you're going from here to here instead of here to here, they're kind of further apart in memory address. Make sense? Everyone's nodding. That's good. If we do the timing of this, you have to be careful with the timing for this stuff. This actually took me a while. I had to rewrite this one last year because I was really trying to be careful to get it right because it's actually kind of subtle to show. So if you move column iteration moving the fastest, it takes 0.6 of a second. If you go row iteration moving the fastest, it takes 0.3 of a second. Both of these guys have constant access, shouldn't matter, but because you're just jumping that further away in the address when you're iterating in the other way, you're going to get cache misses, they're called, where so this detail of how computers are actually implemented will bubble up. And you get a choice about, like, this is common in lots of programming languages. They will typically choose row major or column major, how they do their memory layout for two-dimensional arrays. It's a choice. Julia chose one way. You know, you can have an argument about these things. As soon as there's two choices, people think you did the wrong thing. Maybe half of people think you did the wrong thing. So that you can see going by columns is much faster than going by rows. So 3 times in this case. Please verify. Oh no, sorry, that's a 6 out the front. So sorry, that's 10 times. I'm lying. It's like way slower, which is what you'd expect. Because and worse, I think I had to pick a fairly big array for this one to work. I think I was being cheaty, right? This is one. So I'm trying to make the array shape really like long and skinny so that this is as bad as possible. So this is like, yeah, I lie, but I made it bad to make it look bad. So because I'm deceptive. Please go through and verify this yourself. This is like an easy bit of code to run. So you understand it, pull it apart, have a go at it. Cache misses as you go by. So yeah, the point, teaching point, I'm going to say it again and again. Just because the asymptotic state's constant time, there's different types of constant time. Details of low-level implementation do matter, unfortunately. This stuff's gone easier as computers have gotten better. One of the things that, you know, like you look at when you'll start, if you're doing more software development, you look at the size of the cache for your CPU you're getting. You've got different levels of cache. Has anyone seen that? Like your L1 cache, L2? It's kind of stuff that kind of matters, like how much you can preload, you know, all that stuff helps if it's predicting. They're very, very clever at the low level these days, and I have no idea what's going on. But one of the things is like this sort of stuff used to be worse. Now you can get away with bigger things and being lazy, which is good because you shouldn't have to think about this stuff. As a mathematician doing software, you don't want to have to worry about how a computer works. Unfortunately, sometimes you do. So something as dumb as changing the layout of an array, like if you get a choice about it can be long and skinny or it can be skinny and long, and you know about how you're going to go through this array, might make a huge difference to how the performance. Cool. Okay, I think that's kind of an okay-ish spot to stop for that stuff. I'm happy to take questions. Anyone, any questions on that stuff? No? Everyone's happy? I'm happy to take questions after the lecture as well. If you've got any homeworky things or setup things, please feel free to ask. Otherwise, I'm going to call it. Okay, thank you very much, everyone.